Good morning and welcome to this next lecture on vibrations of plates and shells. So, we are looking at stiffening of a shell by a ring using the receptance method, and we just found the Fn for the ring in the last class. So, the gamma n, corresponding gamma n tilde, let us say, is P by rho A r into omega n square minus omega square. Okay. And then the corresponding eta n is P by rho A r omega n square minus omega square into e to the power j omega t. Okay. And finally, what is the response? The u3n response. Okay. There is no summation over n, we just showed here. Okay. Fn is 0 and non-zero for only n. So, the response is P by rho A r omega n square minus omega square cos n theta, the mode e to the power j omega t. So, we have the response. Once we have the response, what is beta 1 1? This response divided by p cos n theta and e to the power j omega t. Okay. So, that leaves us with 1 over rho A r omega n square minus omega square, that is beta 1 1. Okay. So, we have alpha 1 1 and beta 1 1. So, alpha 1 1 plus beta 1 1 is equal to 2 by rho h l sigma m sine square, I think that is a sine square, yeah, sine square m pi x star over L into omega mn squared minus omega squared plus 1 over rho r a omega n squared minus omega squared equal to 0. Now, one thing I will do is here, the AR multiplied by twice pi A is the ring volume. Okay. Then here rho HL multiplied by twice, I mean HL multiplied by twice pi A is the shell volume. Okay. So, because there is a 0 here, I will divide by twice pi A and twice pi A. So, this is mass of ring, the mass of the ring, and this is mass of the shell. Okay. So, if I can remember, 2 by ms, 2 by mr. Okay, let us see. So, alpha 1 1 plus beta 1 1 is equal to 2 by ms summation sine square m pi x star by L by omega mn square minus omega square plus 1 by mr omega n square minus omega square equal to 0. Okay. So, that is the new frequency equation. Okay. So, now let us kind of plot this term and that term. Okay. let us try and plot that terminus term. So, we will have let us say this alpha 1 behaves like this. This goes up here, okay. Then this goes up here. So, this is shell 1, this is shell 2, this is shell 3, this is shell 4. Okay. And suppose my ring natural frequency is here. That means what? How does it go? Beta 1 has to be in the negative form. So, it will be coming like this from somewhere. Okay. Then it will flip sign and come down like this. Okay. So, the new natural frequencies are the intersections, okay, are the intersections of alpha 1 with minus beta 1. Okay, that means the red and the blue line, red and blue lines. So, we have this is 1, this is 1, this is 1 and this is 1. Okay. So, now you can see the stiffening effect. So, you can see the effect of the ring. Okay, where the ring frequency, ring natural frequency okay, is higher than shell 1 and shell 2, shell 1 and shell 2. Okay. Then those frequencies get raised, those frequencies are raised. Okay. So, you can see that this was the shell first natural frequency, now this is the shell natural frequency. Okay. Now, and this was the shell second natural frequency, this. But now this is the second shell natural frequency. So, both of them got raised from here to here and here to here, okay, or rather on this axis here, from here to here, from here to here, that is the way to look at it, yeah. So, that is the increment. Whereas, this is the shell third natural frequency, the shell fourth natural frequency, okay, and this is the ring frequency, ring natural frequency. which is lower, than this value, it's lower than this value. Then what happened? This now is the new natural frequency, so that got lowered. This is the new natural frequency that got lowered. Okay. So this ring frequency or ring, what it does when it's above the shell frequencies, it pulls them up. Whereas when it is below, okay, when it's below this and below this, it pulls them down. To here, okay. Now a little bit more insight. Suppose the change from the original, omega mn to omega k is small. Okay. Then at omega k, the 1 over omega mn square minus omega k square alone dominates. Okay. This equation here, let me repeat if that is not clear. This equation here has many solutions for this omega, which are omega k's, and k running from 1 to etc. Okay. And if it so happens that the ring is not a very strong stiffener, doesn't influence very strongly, then omega k is going to be close to omega mn, right. If the ring was not there at all, then every omega is omega mn, they don't change. You can see that, right. If I drop this to 0, this is the only term I have, then every natural frequency, every omega is omega mn. Okay. But because of the presence of the ring, there is going to be a shift, and if that shift is small, then whenever there is you put an omega k that is close to 1 omega mn, so that term will dominate. Okay. So if we now look at it that way, so without the summation, twice ms sine square m pi x star by L by omega square mn minus omega square plus 1 over mr omega n square minus omega square is equal to 0. If I can remember this on the next page, okay. Let's see, 2 by m shell sine square m pi x star by L omega square mn minus omega square plus 1 over m ring omega n square minus omega square equal to 0. Okay. So let us say this is omega k now, omega k. So what do I have? I have twice over ms sine square m pi x star by L is equal to minus 1 by mr omega n square minus omega k square, and I have 1 over omega square mn minus omega square k. So if I say twice m ring by m shell sine square m pi x star by L, okay, into omega n square minus omega square k is equal to omega k square minus omega square mn. Or I could have done it better. It's okay. So what I have now is omega k square 1 plus twice m r by m s sine square m pi x star by L is equal to twice m r by m s sine square m pi x star omega n square plus omega square mn. Okay. So if I divide this and multiply by omega square mn, omega square mn, omega square mn. Okay, so what do I get? I get twice mr by ms ms sine square m pi x star by L into omega n square by omega mn square 1 plus into omega square mn is equal to omega square k 1 plus twice mr by ms sine square m pi x star by L. So if I put it in a convenient form, this is what we are looking for as a perturbation to this. Okay, so what happens? My omega square k, the perturbed natural frequency, is omega square mn into 1 plus twice ms by twice m ring by m shell omega n square by omega square mn sine square m pi x star by L divided by 1 plus twice m ring by m shell sine square m pi x star by L. Okay. So this is under the assumption that the ring that is stiffening, okay, that's stiffening the shell, is not, influencing the resonances very strongly, so that a single term in alpha 11 dominates. Okay. So now you can see over here that if omega n is greater than a particular omega mn. Okay, omega n is greater than a particular omega mn. Now this term is the same as this term is the same as this term is the same as that term. This is the only term. So if omega n is greater than omega mn square, then this term is bigger. Okay, so that means this is multiplied by something bigger than 1. So omega k is bigger than omega mn. So then that means omega k will turn out to be greater than omega mn. So omega n is higher than omega mn, so it will pull up the natural frequency. Okay. Whereas when omega n itself is less than omega mn, okay, then the numerator is smaller than the denominator. All terms remaining same, this is smaller than 1. So the numerator is smaller than, this numerator here is smaller than the denominator. And therefore omega k is smaller than omega mn, okay, which means omega k is going to be smaller than omega mn. Okay, that is the ring stiffening effect. Okay. Now along these lines you can have a shell, okay, and then you can have multiple stiffeners. You could have multiple stiffeners. Okay. Then you will have a matrix of the kind we saw for the springs. Okay, alpha 1 1 plus beta 1 1, alpha 2 2 plus beta 2 2, alpha 3 3 plus beta 3 3, and these rings are independent. So the cross receptance will not be there. So this will just be alpha 1 2, alpha 1 3, alpha 2 1, etc., etc. Okay, and then you will have the three amplitudes, forces F P1, let's say P1, P2, P3 going to 0, and then you will find the new set of resonances, and from there the dependent force amplitudes, okay, that should be applied to the shell at each ring location to find the new mode shape. The setting of this determinant to 0 will give you the new natural frequencies. Okay. Then each natural frequency, the dependent value of P1, P2, P3 is the force value that should be applied to the shell at the new natural frequency. That will give you the new mode shape. Okay. So receptance is a very powerful method. I've told you many other things last time. You can even do natural frequencies, and modes when there are voids in a system, when small voids are there in the system. Okay, so you have a plate, and then now what you have, original plate, then now what you have is you have taken out some material, all chunks of material you have taken it out. Okay, then you can find the effect of removal of this material, and you can find the new natural frequencies and modes. You can do that too. Okay. So with this I close the section of receptance. Okay. There is a lot more in the text. So as they say, anything can be learned, but not everything can be taught. Okay. So receptance, there is more material in the text. So I advise you to read it. Okay. So I will close this lecture here. We will continue in the next class. Thanks.